Hello everyone, I am a postdoc researcher at the University of Michigan, and today I will talk about my recent paper which was published at the Astrophysical Journal Supplementary Series. In this work, I determined the physical condition and chemical analysis of a sample of planetary nebula around Wolf-Rayet centers using collision ionization, collisional excitation line, and optical recombination line, which collected with IFU instrument on Australian National University telescopes. Although most centers of planetary have hydrogen-rich surface and is considered fractions of them, around 25% of them show hydrogen deficient surfaces, and they show carbon and oxygen abundance. And there is a suggestion that they could be related to poor Einstein scenario or very late thermal pulse. And for this work, I use optical intergraphite units instruments on the Australian National University 2.3 meter telescopes, which has a field of view of 25 times 38 arcsecs and a resolution of 3000 and 7000. And this is it. You see the example of the sample which I observed, and the rectangle show the aperture used to extract the integrate flux spectrum of each objects on the field of view of IFU. And this sample has a wide range from early type, which has hot temperature VO1 to VO4, and to late types, which has cool temperatures. And to extract flux, I use an ideal library on each object and filled multiple Gaussians, and then I obtained logarithmic extension, which I use to correct and direct the flux emissions. And this direct flux emission used to obtain the physical conditions, and I obtained the nebula electron temperature and density from collision excitation lines by solving level populations, and then I propagate the uncertainty using the Markov chains Monte Carlo methods. And in this figure, there is a diagnostic diagram of one of them. You can look at the other one in the paper. And using the self-consistent methods and the approach which include an iterative waves, I provide I constrain the physical condition, density, and temperatures. And in these figures, you see the result of electron density obtained from single ionized forbidden lines plotted versus the nebula H beta surface brightness, and the dashed lines show fits to these objects. And this is an agreement with theoretical predictions that surface brightness related to density square, and surface brightness decline with radius as nebula expands and density drops. And on the right, you see the temperature of oxygen 3 over nitrogen 2, which plotted versus excitation class based on equation defined by Dopita 1990. And you see there is this correlation is suggested there is a trend with excitation class, which can explain by radiation field from central source. So at the higher radiation, we had higher temperatures. And using the fact that emissivity of heavy element optical recombination have a relative big dependence on electron temperature, also we can also use a recombination line to constrain the temperature and density. And using these methods, which is based on minimization difference between normalized flux intensity and normalized value predicted by theoretical methods, also obtains the physical condition from optical recombination lines. And on this figure on the line show where there is a minimum value of less square value, so that associated with best fit parameters. And here is a summary of physical condition. And this self-consistent plasma diagnostic of heavy elements optical recombination line of nitrogen to an oxygen 2 stage, so there is a small fraction cool and dense material in some objects. And the other thing that I obtained the ionic analysis from collision excitation lines and using the collision strength and transmission probability, and also obtained the ionic abundance from optical recombination line using the effective recombination coefficients.
3 minutes, please.
Okay. And here you see the correlation between the abundance excitation factor and temperature difference, which is difference between forbidden line and recombination line, helium bonds. And these correlations likely confirm the previous suggestion there is a fraction of cool oxygen-rich dense clump material in diffuse warm ionized gas. And also I obtained there is some correlation between temperature difference and surface brightness. And this anti-correlation likely suggests that temperature difference is weakly related to nebula evolutions. And there is also correlation between abundance dispersion factor of oxygen and nitrogen. But however, we should know that the most nitrogen 2 lines are contaminated by resonance, fluorescence excitation in some objects. So this contributes to this correlation is very weak. And as you see there is most result has consistent with oxygen-rich materials. And also I compare the result to AGB models, and here you see this is consistent with AGB model of between 1.5 to 5 solar mass, and some objects have type 1A, which has experienced the hot bottom burnings, which occur in the solar mass, horizontal to solar mass higher than 4 solar mass. Other thing, I recently also posted another paper which related to morphokinematics of these objects, and I use velocity channel maps and position velocity diagram to constrain 3D morphokinematics of this object. You can look at the archive of this paper. And in future works, I plan to present the ionic map of this object. The ionic map currently are available in my PhD thesis, and this may help us to understand better the origin of abundance scaling band store in some NPN around Wolf-Rayet central star. And here is my last slide and is summary of my key finding. And if you have any question, I can answer.
Thank you very much.